Hello, we are students from MAHSA University, and this project is in collaboration with UCSI. I'm Ammar Danish.
I'm Aravind Shankar.
And I'm Huda Raihanah. Our project is about finding a safer way to degrade crystal violet using a biocatalyst, and this project is supervised by Dr. Nurul Nadiah.
To begin with, what is crystal violet? It is a recalcitrant dye molecule which produces toxic effects to the environment. Its applications are in laboratory fields like microbiology, histology, and cytology. Other applications are in the textile industry, photography, antifungal growth, and ink production. The removal of crystal violet using physiochemical methods produces harmful byproducts. So, when it comes to environmental impacts, it is known to have toxic effects on aquatic ecosystems and potential impacts on the food chain. The dye can resist degradation, and its accumulation in soil and water can pose long term challenges.
The objective of this innovation is to provide a cheaper, faster, and less harmful method of removing crystal violet from wastewater.
And the solution to that is lacase, an enzyme extracted from different types of fungi, bacteria, insects, and other plants. It works by facilitating the transfer of electrons from the substrate to molecular oxygen, leading to the oxidation of the substrate. This makes it a versatile enzyme with multiple potential applications in 8 different areas, including medicine, bioremediation, industrial, and food processing.
This project is unique as it incorporates lacase enzyme in the wastewater chemical reactor, allowing for better removal of crystal violet. This is because, unlike the physiochemical method, lacase enzyme targets specific substrate on crystal violet, which increases the reactor's efficiency. By incorporating lacase enzyme in the reactor, it requires less energy, has no toxic byproduct, and is easily modified for future improvements.
In order to prove that lacase enzyme has the ability to degrade crystal violet, an experiment was performed which included 5 steps. The first step involved the preparation of reagents which include the phosphate buffer, made by mixing dipotassium hydrogen phosphate with distilled water. The purpose of the phosphate buffer is to provide a stable environment for enzymatic reactions. This will allow us to study and manipulate the enzyme lacase under controlled conditions. Then came the preparation of the crystal violet stock solution, which is later used to make 3 different concentrations of crystal violet. These 3 different concentrations were then put into 3 separate test tubes for each concentration. This was done to optimize the reaction conditions for lacase. This includes finding the concentration of crystal violet that yields the maximum reaction rate, or one that will allow the most sensitive detection in assays. After that, an equal amount of lacase enzyme was added into each of the prepared test tubes. Each test tube from the 3 concentrations were then incubated at different temperatures using a water bath. The temperatures used were 40, 50, and 60 degrees Celsius.
Moving on to the results, it can be observed that crystal violet degrades fastest at higher concentrations and temperatures, with the optimum degradation at 50 degrees Celsius. The thermokinetics of lacase enzyme, including initial rate, Gibbs free energy, enthalpy, and entropy, were measured. These parameters are crucial in designing chemical reactors where optimal conditions such as temperature, concentration, reaction rate, stability, and heat transfer will impact the efficiency and performance.
By creating a reactor that integrates lacase enzymes, the process of wastewater treatment is improved, the amount of toxic compound in the wastewater is reduced, and less resources are needed. Not only will this improve waste management of every industry that uses crystal violet, it also improves public health and reduces the overall environmental footprint.
Various industries are looking for a more sustainable method to manage their crystal violet disposal. The unique properties of lacase is just the solution they need. Lacases work under mild conditions and use molecular oxygen as the primary co-substrate, producing water as the main byproduct, making the process more cost-effective and produce lower environmental impact. This aligns with the growing demand for sustainable and green technologies, allowing for a huge commercial potential of this enzyme.
Thank you for watching.